Welcome back to ECE 501B. Homework number 2 is due tomorrow. You can turn it in early without penalty if you want, and I will try to remember to collect those. Homework 3 is coming soon to a D2L box near you, and hopefully it will be in your particular D2L page. Yes. Is that what they are? Oh, this one's due at 4. I'm getting my times mixed up, so I need to open up the mailbox or Dropbox a little bit more if you want it available until 11:59. It really makes no difference to me, so I'll try to remember to make that open until, and if I forget, put it into the generic Dropbox. I think I have created a generic Dropbox that you can use if something crashes or if it doesn't work, if it's 11:58. You hit the submit button and it doesn't go through, just like something this might happen, then submit it in the generic Dropbox and I can sort of see the timeline on that, and hopefully I won't hold that too much against you. There is new material that happened between Monday and today that is on the D2L website on the concept of dimension, which is the last piece of chapter 2, and I think I've labeled that as something in unit 2.3. I think that's the third piece of information in unit 2. Today we are starting unit 3, which is so far still consistent with the chapters in the book. We will begin talking about chapter 3 in Axler, and that is dealing with this concept of linear maps. We'll talk a little bit about the properties of linear maps, or what those need to possess in order to be a linear map. We'll illustrate that with some examples. There's all sorts of examples. We'll pick some of those, some from Axler, some from space, maybe not a vector space, but from some other space. Maybe we'll have some non-examples of linear maps. We can also create a vector space of linear maps. So once we have a set of linear maps going from some vector space V to some vector space W, that set can be viewed as a vector space. Then we'll get into some concepts you've maybe seen in the matrix setting. We'll discuss those in the generic setting of linear maps, and those are null space and range space, some important subspaces to keep track of. Let's then start by talking about what we're dealing with in terms of chapter 3. This notion of linear maps. We can say that a linear map is really the following sort of picture. You could sort of think of it as something going between two different vector spaces, a vector space V and a vector space W, and that map is now this linear operation between a vector space V and a vector space W. This is sort of a conceptual way of viewing the following. It's really just, so if I continue with this line of thought, a linear map is a function that's really taking some element in V and mapping that into an element in U. Or I think maybe, boy, I can't get my letters right. Let me call this, so you just have to add another bump to yours. Now it's a W, not a U. Hopefully you didn't have to change too much if you're taking notes in ink. So now we're going from V to W. A linear map is a function that's going to take let's say as its input, an element of vector space V, and uniquely identifies an element of vector space W. And that's what we tried to show graphically. And we might then represent that symbolically. We have this linear operator T, or a linear map. Let me not say operator yet. We'll use that description for a specialized linear map. Here is the map T, and that's now taking an element from V and mapping that into an element of the vector space W. We're going from V to W. That's our notation. Now, to be linear, it's going to require that it satisfies two properties, and you can sort of anticipate what those properties are going to be. This linear map then is required, or let's say requires, two properties to qualify as a linear map. One is what's referred to as additivity, and that says that if we operate on the sum of two vectors in our, let's say, domain vector space, capital V, those being U and V, that's the same as taking the sum of those two maps, TU plus TV. So we want that property. We want T of the sum of two vectors to equal TU plus TV if U and V are coming from the vector space V. And we also want a property referred to as homogeneity. And that's saying that if we have a scalar scaling a vector from our vector space, if we now take that through this linear map T, then that's the same, or it's equivalent to that scalar times T times V. So together, those two properties are needed to make this mapping linear. So we could have any map we wanted, but to make them linear, they need to satisfy the two properties of additivity and homogeneity. And I'm probably going to get a little bit sloppy with the notation, and the notation is probably going to get overloaded also with different forms of zero. But for now, let's say we may mix notation, and this is what the book says. We might do something like T operating on V through this parenthetical notation, or we may just say TV. Another notation that the book uses is this script L, and that's really defined to be the set of all linear operators between the vector space V and the vector space W. Even though we have maybe this mapping satisfying these two properties of additivity and homogeneity, that still gives us a huge set of functions that are linear maps. And let's look at some of those. So this linear map is large or broad. Let's look at some examples, first from Axler. The first one that he talks about is the zero map. And I think you can anticipate what this is going to do. This is actually going to take every vector in the vector space V and map it into the zero vector in W. This now maps all elements in V or of V to zero, or what we call the additive identity in W. Notationally then, that map might be just called zero, and that's now going to be operating on V, and that takes us into zero. But those zeros are different. In this case, this zero on the left is actually symbolically representing the map from the vector space V to W. This zero on the right is the additive identity in the other vector space, sort of the range of the operation. That's the additive identity in W. And V belongs to the vector space capital V. And capital V could have a different dimension than capital W. Those vector spaces don't have to have the same dimension. And that's what I'm meaning by we've overloaded the notation. Which really means we're using the same symbol to mean different things. That zero means a lot of things. That said, it might be nice to have a zero operator, something that maps everything into zero. Another one that's closely related to that in terms of its sort of, what do I want to say, its generic properties, and that's the identity operator. Keep messing up and saying operator. Don't let me do that. Identity map. The operator is going to be reserved for when we start in V and end back up in V. That's when we're using an operator. So try to keep me honest. Right now, today, we'll probably just be talking about maps. So these linear maps are taking us from V to another vector space W, not necessarily back into itself. But in this case, it is an operator. It's the identity operator. It's a linear map because you're going from V back into V because it's the identity map. Can we get any more crazy with our terminology? But this is now maps each element in the vector space V into itself. Meaning if I now say IV, that's now going into V. Another linear map that is discussed in Axler is the differentiation map. Meaning if we now have this linear map T that's mapping, let's say, between, is it clear what I'm meaning by that? Do you remember my notation? This is the set of all polynomials operating on the real numbers. So they could be any order polynomial. And this T is supposed to be the differentiation operator. And we could say, well, let's just not get too specific right now. Let's just say that that maps back into itself, the set of all polynomials with real coefficients. That means then that if you had a P of X belonging to, pulled from this set of polynomials, then if you operate on that, we'll just say that that's P prime, the derivative of P with respect to X. And that's a linear map. And I think you know that because of what you've done in calculus, for example. If you looked at the derivative of a sum, what's that equal to? The sum of the derivatives, isn't it? Especially if those are polynomials. This is easy to sort of think about or verify. Also, if you take a scalar and scale a polynomial and then differentiate that combination, that's the same as taking the derivative of that polynomial and scaling it by a. That's another linear map, is this differentiation. And we can go the opposite way. We can also talk about a linear map of integration. And we could even think about two different varieties. We could have the indefinite version, which says that now our map T is an element of this linear map between, and let's just say that we're dealing again with polynomials with real coefficients. If we do an indefinite integral, we end up back with a big polynomial, don't we, when we integrate? So we're going to end up with W being back into this vector space of polynomials. But if we looked at the definite integral for our linear map, then we're evaluating that polynomial at set limits. And then we're just going to end up with what? We're going to start with a polynomial of some order pulled from the set of all polynomials. Then if we do a definite integral, let's say we integrate that from 0 to 1 dx, what are we going to end up with? What space are we going to end up in? Pardon? The real number, or a real number line, right? That's where we're going to end up on, as the real number. So now we would be simply going from the polynomial, the set of polynomials, to the real line if we have a definite integral. We can with a linear map, we can actually change dimensions. By that, for example, suppose that we have this linear map T that's going to take us from three-dimensional space to two-dimensional space. Meaning, suppose that we define T operating on X, Y, and Z to push us into another vector space that's maybe defined by 2x minus y plus 3z. That's the first coordinate in a two-dimensional space. And the second coordinate, let's say, is another combination of the original three coordinates, 7x plus 5y minus 6z. So we're going from a three-dimensional space, x, y, z, into a two-dimensional space by this linear map. And you could show that this linear map is linear. It satisfies additivity and it satisfies homogeneity. If you looked at different combinations of x, y, and z, for example, you could take two and then you could scale one of those. Let's look at another map that's related to this. Let's say the projection map. And this one really is, let's say, taking three dimensions back into three dimensions, but maybe we're only going to live on one plane in the final result, even though we're in three-dimensional space, theoretically. Meaning, suppose that we define T of x, y, z, we take any point in three-dimensional space, and we simply map that onto the xy plane. So now we might say, is this actually linear? Yes or no? Or do we want to just try to directly show this or prove that? What do we need to show if we want to verify that this is a linear map? What's going to constitute something being a linear map? So we have to have additivity and homogeneity. Let's look at those two separately. If we want additivity, then let's just pick a couple of points. Let's pick U, not YOU, but the letter U for a vector. Maybe I will have U come up, and then we can act this out, right? So we would have U1, U2, and U3. That's like who's on second. I don't know. Anyway, so we now let U equal U1, U2, and U3, and V, another point with coordinates V sub 1, V sub 2, V sub 3. And again, this is maybe overloading the notation. In this case, U1, U2, and U3 are scalars in some field, and they're forming a vector U. U1 is not a vector itself. Is that okay? So these are all in three-dimensional space. Now we want to look at T of U plus V. And that is just going to be T of U1 plus V1, U2 plus V2, and U3 plus V3, by definition of adding those two vectors, U and V. By definition of this map that we're trying to show as linear, what's the result of operating on that 3 vector with t, by definition of how we defined our projection map? We just keep the first 2 coordinates and throw away the third one, right? Or set it equal to 0. So we end up with that. Are we okay with that? Now we can pull that apart. We can say, well, that's made up of U1, U2, and 0 plus V1, V2, and 0. But that's just T of U1, U2, U3 plus T of V1, V2, V3, which is just T of U plus T of V, and that's going to verify our additivity. We needed to show that T of the sum is T of U plus T of V. So we did verify additivity, and sometimes you can show one and not the other, but you have to show both in order for it to be a linear map. If we now look at homogeneity, now let's just pick an alpha as our scalar. Now we need to show that T of alpha U, which is T of alpha U1, alpha U2, alpha U sub 3, is now alpha U1, alpha U sub 2, 0. But we can factor that alpha out. And this is now alpha times T of U1, U2, U3. But that's just alpha T of U. And that now shows that homogeneity is true. So T, in this case, our projection map is linear. What about a translation map? We want to go from English to Spanish. No, this is translation in position, right? So we're not translating languages yet. We're translating points in a 3-dimensional coordinate frame. Let's say that we now are going T, and let's not get too worked up. Let's just do it in a 2-dimensional plane. Let's say we're going from R2 to R2 with this linear map, or this map. We want to check and see if it's linear. Suppose that now T of U1, U2 is U1 plus 1 and U2 plus 2. Is the translation map linear? Anybody bring a coin? We could show this the way we did before. Let's try a different approach. Let's see if we can find a counterexample that actually will show that it's not linear. And the counterexample that you could use, if it works for you sometimes, is to see, is the additive identity going to map to 0? And if it doesn't, then we don't have a linear map. The answer is actually no. It's not a linear map, and let's see if we can produce a counterexample. And that counterexample is really going to answer the question, is the additive identity mapped onto itself, where this additive identity is the zero vector. Meaning if we start with t and operate on the zero vector, which is 0, 0, u sub 1 is 0, u sub 2 is 0, from our map, from our translation map, what does that end up being? That ends up being 1, 2. And I hope that's clear that that's not 0, 0, which we could maybe shorten to be 0. And so this map does not satisfy homogeneity. Meaning that's really what's going on here, one way of viewing that. If a map is linear, then it should satisfy homogeneity, which we can show via this additive identity property. A linear map should map the additive identity onto itself. And what we're going to do here is use a couple of ideas that we've already been discussing. From homogeneity, what do we know has to be true? If I operate on AV, what's that supposed to be? A times T of V, right? If it's a linear operator or a linear map, And we also are going to use several times, we're going to apply proposition 1-4, and I'm guessing everyone has that memorized. Proposition 1-4 was an overloaded result, which says take the zero scalar and operate or apply that to any vector, and you'll get the zero vector back, or you'll map that into the zero vector. That's proposition 1-4. All right, so now we can, for a linear operator, we can basically say let A equals 0, which is a member of our field of either real numbers or complex numbers. And we can take any V we want, any vector, in V, in capital V, our vector space. Doing that, then we can say T of A, which is 0 times V. So in this case, this is now our zero scalar. That's equal to T of 0, and that's proposition 1-4. But by homogeneity, that's supposed to be 0 times T of, or A times T of V, where this is now our A again. here is our homogeneity step. So really we're sort of, by homogeneity, we have this T of 0V is equal to 0 T of V. And by Prop 1.4, we have T of 0V equals T of 0. And now we just use Prop 104 again. Scalar times a vector, which is what T of V ends up being, a vector, is equal to the 0 vector. So again, this is another use of Prop 1.4, and now we have that element being a 0 vector. But this now says that T of 0 needs to equal 0, meaning the additive identity needs to map into itself for a linear map. This is kind of fun. Let's do something else. Let's look at norms and linearity. And we haven't really talked about norms. We'll discuss those later, but let's just define some of those. Norms are a way of measuring length or size of a vector. And let's now look at norms and linearity. And this is sort of jumping ahead, but maybe this will allow us a little bit more insight when we start looking at inner products. And if we want to preserve linearity, then maybe we want to use something related to norms, but maybe not quite a norm. And maybe this will sort of, if you remember this discussion, you'll go, oh, maybe that's why we can't use a norm when we're looking at this particular part of the course. So these norms, we'll discuss those later. But you already know these concepts, I think. Let's, in talking about that, let me just define x. And now again, I'm going to now use the subscripts as coordinates. X is now some n-dimensional vector, x sub 1, x sub 2, up to x sub n, where each of those x's are coming from our field of numbers, either the real numbers or the complex numbers. X is just an n-dimensional vector. Here are some definitions. Do you remember what the one norm is of a vector? Symbolically, I might write that as x double bar sub 1. Have you seen this? Do you know what the one norm of a vector is? You know what the two norm is. The two norm is your Euclidean distance, isn't it? That's, if you were in two-dimensional space, that's the hypotenuse. That's the length of the hypotenuse. That's the two norm. That's the sum of x squared plus y squared square rooted. That's your Euclidean norm, or the two norm. The one norm is like that. It's related to that, except now in the two norm, we squared things. In the one norm, we raise everything to the one power. And what were we squaring? We were squaring coordinates in the two norm. In this one, we say just take the magnitude of x sub 1 and raise it to the one power. That's what we're doing. Plus x, the second coordinate. And we just keep doing that. And then we take what? Then we raise that whole thing to the 1 over 1 power. which we don't have to do anything, right? If it's 1 over 1, that's 1. So this is now the 1 norm, the sum of the absolute values or the magnitudes of each of the coordinates. And the reason why we're taking magnitudes is, one, they could be negative, or in complex, we need to make sure that we're just dealing with numbers to get some idea of size. That's the 1 norm. The 2 norm, which is what I was referring to before, that's now we take x1 and square it. We take the second coordinate's magnitude and square it, and we keep going. And then we raise that to the 1 over 2 power, or we take the square root of it. And this is now, for a two-dimensional vector, this is x1 squared plus x2 squared, square rooted. That's our hypotenuse of a right triangle. Or we could then say that this is now this square root of sum of magnitudes of the individual components squared. And now, can you predict what the 3 norm would be? The 4 norm? The 5 norm? How about the infinity norm? What's the infinity norm? So all of these have a pattern. I hope you can see that. We take the magnitude of the components, raise them to whatever norm we want in terms of value, and then we sum those pieces up, and then we raise that sum to the 1 over whatever norm we're interested in, power. And so the 3 norm would be those cubed, sum those up, and raise that to the 1/3 power. The infinity norm have you guys seen this before? These norms? Yes, no, maybe not. Okay. What would you guess this to be? 1? One little, I don't know, 1 finger, 1 digit? So what happens if we carry this process to the extreme? Meaning, if you now have a vector and you say, okay, take the magnitude of each of those coordinates and raise each of those to a really large power, what's going to happen? It's going to blow up, isn't it? But is the biggest coordinate in magnitude going to dominate? Meaning if I had, let's just take some numbers, 1, 2, and 3. Those were my coordinates. Now I raise 1, 2, and 3. Those magnitudes are just 1, 2, and 3, but I raise those to bigger and bigger powers. Which one of those coordinates is going to get bigger faster? The 3, right? The biggest one. And then what I'm going to do is I'm going to sum those up and then just take the 1 over some large power root of that. But what's happening is as I take that to the extreme, the 3 is going to be the only thing that you're going to see. You're going to raise that to a huge power and then just take its reciprocal root, basically. And so what you're going to be left with is the maximum of the coordinates magnitude. Meaning, if you had n coordinates in a vector, the infinity norm is just going to look at the largest one when you look at the magnitude of those coordinates. So this falls out. There's your 1. It's 1 coordinate of your n-dimensional vector. Okay? So that's your infinity norm. There's your 1, 2, and infinity norms. If you're reading papers and they start talking about the infinity norm or the 2 norm with respect to vectors, this is how you could find, or this is what they're referring to. Okay? Now, where was I going? Where were we? We were discussing maps, weren't we? Well, you could view these as maps, couldn't you? You could say this is going from an n-dimensional space into what? What is this going to give you, this infinity norm? A real number, isn't it? It's actually going to be a non-negative number. What about the 2 norm? Same thing, right? So we're going from an n-dimensional space to a number, and that's really related to the size of this vector. If you think about, just draw a picture and say, give me a 3-dimensional vector, and I can talk about the size of that vector in terms of its 1 norm, 2 norm, or infinity norm, and they're all three going to give me some feel for the size of that vector. Yes? Now, let's ask the following. Is the 2 norm linear? And I didn't scroll it quite all the way off. The 2 norm is sitting there staring at us in its formula. Is that a linear relationship between r to the n to r? As a mapping, this t, let's say, is now the 2 norm, and maybe we could just say, well, does it work from a 2-dimensional plane down to the real number? If it's linear, then it needs to have a couple of properties, doesn't it? Additivity and homogeneity. Let's just see if we can find a counterexample to show that indeed this is not a linear map. We can show with, let's say, x equal 1 minus 1 and y equal, so I'm really playing fast and loose with my vectors, aren't I? X and y now are 2-dimensional vectors. It's not the x coordinate and the y coordinate, so you'll get used to doing weird things. I could have called this an x sub 1, and then it would be a vector instead of a coordinate in my definitions for norms, right? But hopefully you see by context what I'm dealing with. Here I just labeled it x, 1 and minus 1. So in that case, x sub 1 is 1, and x sub 2 is minus 1. They're in the real numbers. Y has 2 coordinates, y sub 1 and y sub 2. And I hope it's clear that you can show with this that looking at the 2 norm of x plus y, which gives you a vector of 2, 0, that's not going to have the same length, is it, as x 2 norm plus y's 2 norm. So we're going to violate the additivity result. Meaning here, what's the length of x plus y, or what's the 2 norm, I should say, of x plus y? X plus y is, as a vector, 2, 0. So now I have a triangle that has what? A horizontal length, and what's my vertical length? It's vertically challenged, isn't it? It's 0. So the hypotenuse is the same as the horizontal. The hypotenuse is 2, isn't it? So we would have 2 squared square rooted. 2. What's x1? What's the length of this in the 2 norm? Root 2, isn't it? Square root of 2. What's the length of y? Square root of 2. So now we have 2 is not equal to the square root of 2 plus the square root of 2, or 2 times the square root of 2. 2 is not equal to 2.484, or whatever it ends up being. 282 or something. Okay? All right. Now, let's move on and talk about, those were examples of linear maps and some that weren't linear maps. We can also turn these linear maps into vector spaces. So we're going to turn the set of linear maps, which notationally we refer to as L of VW. We map from a vector space V into another vector space W. Into its own vector space. Remember how we had vector spaces that could be matrices, or they could be functions, how we define different vector spaces, and what did we, so this is now, and we had polynomials forming vector spaces. Now we have a set, and that set is made up of linear maps. Each of those linear maps is now a vector, right? In our vector space terminology. So if you have a map T in this linear map from V to W, we may have another T sub 1, another T sub 2. That set of maps, now we are going to allow those vectors to form a vector space. Meaning this is another example of what you could think of as an abstract space. Meaning we now have a set of vectors which are the elements of this set of linear operators from V to W. So we have a set of vectors, and we have a set of, we need scalars, don't we? And those might be coming to us as from the field of real numbers or from the field of complex numbers. So we have a set of vectors, we have a set of scalars, and now what do we need to be a vector space? Remember the definition of a vector space? It had 3 things, didn't it? Sort of had vectors, and then we had 2 properties, addition and multiplication. Addition of the vectors and scalar multiplication. So that's what we need to see or to produce in order to convert these linear maps into a vector space. So we have a set of vectors, those are the linear maps, and a set of scalars belonging to the real field of real numbers or the field of complex numbers. Now we need our two binary functions. Plus and multiplication. The plus is our vector addition, and this dot is our scalar multiplication. And we just need to agree on what we mean by those additions and multiplications. One, if we have S and T both belonging to this set of linear maps, then we can simply define what we mean by addition. So we can define S plus T to belong to this set of linear maps, where S plus T operating on V is now going to be S operating on V plus T. Whoops, that's supposed to be a V operating on V. For all V in our domain set of vector spaces, or vector space V. Then for the scalar multiplication, we can pick an alpha in F and a linear map in our vector space, or I'm sorry, in our set of linear maps, and then alpha T is going to then live in that set of linear maps, and we will simply say that's because alpha T operating on V is going to equal to A times T V. And with those two properties, that now satisfies all of our properties of a vector space. What's our additive identity? In this vector space? Yes. So now the question was, doesn't this need to be closed under addition? And that's what we're saying right here, is S plus T is going to be an element of our linear map, But then we're saying we're defining this sum to be the individual pieces, the linear map on V plus T as a linear map, and those two belong to this, and that's how we're going to define our sum of two linear maps. And this is guaranteeing that it's closed under addition. Yes, so it needs to be closed under addition and closed under scalar multiplication. And this is how we are defining those two pieces. Here's our addition piece. S plus T, we're just going to say is S of V plus T of V. And then on the multiplication piece, alpha T operating on V is going to be the same as scaling. Whoops, and that's supposed to be an alpha. That's then going to be equal to alpha T operating on V. That's the way we're defining our addition and scalar multiplication. And with those definitions, now we have created or built a vector space out of these linear maps, or the set of linear maps from V to W. If that's okay, what's the additive identity? Okay, so now we don't need to worry about taking 0 to 0 so much. It's going to take everything to 0, isn't it? So now we want the 0 map, and that will be our additive identity. So yes, we want something to always be going to 0. So now the 0 map is going to provide that for us. And that's a part of our linear maps from V to W. We have the 0 map. And that's what we overload with this 0 in terms of notation. The answer then is the 0 map, which we've defined to just be this 0. Now, it actually happens for some of these pairs. If you take two linear maps, you can pair them up and actually sort of concatenate or do a product of those or a composition of the maps. Sometimes that makes sense. So for some pairs, of linear maps, we can even define multiplication. And if you want something concrete to think about, you could start thinking about these linear maps being matrices. And that's sort of the next step in this process after we talk about null space and range space. But if we're given a linear map T, that's now belonging to this set of linear maps from V to W, and we're given S, and now it's also living in another set of linear maps. Well, what am I doing? Let me start over. Hopefully you're not that far. Let me go from one to another. Let me say we go from U to V. And now what do I need to do? If I'm going to operate on a vector U, that's going to put me in a V. Then I want to operate on that with S, another operator. So now I need to start in V and go to W. So now I can go alphabetically, UVW, maybe a little bit easier. So that now ST is going to be a linear map from the original beginning vector space U into the final vector space W. Meaning now we can take this ST on V is equivalent to S operating on TV. And I think it's clear that this is only going to work when the first map takes us into the space of the domain of the second map. Meaning this only is going to work when the output space of T is putting us in the input space of S. And maybe I'll refer you to Axler for more, but what you can think about is if we're thinking about matrices, what do you know about matrices and multiplication? Or one thing that you've always been forewarned to maybe pay attention to when you're multiplying matrices versus maybe some real numbers. If you multiplied two real numbers, A and B, that's the same as B times A, isn't it? But matrices, all bets are off, aren't they? It's not necessarily commutative. And that's the same with these linear maps. They may not commute. It may be much different if you take whatever we started with, T and then S versus S then T. You may not get the same result. And that's what I'm saying here, is this multiplication is not necessarily commutative, or that may not commute, meaning this ST sort of product is in general should be the same as ST, but it may not be the same if, boy, as TS. And that's because of what you already know dealing with matrices. You can sort of find examples where that's not true. Now, it is true if you have diagonal matrices, isn't it? As long as they're dimensionally compatible. Meaning, what am I meaning there? The columns of S are equal to the rows of T, then those matrices are compatible, but then you need the other to be true also. You need T and S to be compatible that way. Let's now look at some properties of these maps, and in particular, this notion of null space. The null space of a linear map is the subset of the input space. That's this vector space capital V. So we're looking at a subset of that space that maps to the additive identity in the output space, that maps to 0 in the output space. And I like to sort of think in pictures, meaning if this is now our input space V, and maybe this is W, our output space. We are worried about or interested in what's happening when we map from V to W. But the null space is actually concerned with a subset of V, which this is now going to be called the null space, or we may just say null of T. All of the points or all the vectors in there are going to go to 0, to 1 point in W. So this is now our zero vector, meaning you maybe start with a vector V, and that now mapped through T goes to 0, 0 vector. This mapping T might be a matrix. Maybe it is 2 by 5. Didn't want to use a wood example where it was a 2 by 4. So it's a 2 by 5. If you're a carpenter, you know you have 2 by 4s, 2 by 6s, 2 by 8s. I took a 2 by 5. Okay. So now we have a 2 by 5 matrix. That's mapping. What's the size of our vectors in V? If I have a 2 by 5 matrix T, what is in V? What are the sizes of, what are the dimensions on my vectors in V? Really? Okay. So if, let's say that I have a matrix A that's 2 by 5. That now looks like this, doesn't it? It's 2 rows tall and 5 columns wide. That says then that V is my vector here that has to have as many rows as T has columns, doesn't it? So this is my V, and V is a 5 by 1, isn't it? Vector. What's my W? If this is now my A, there's my V, and here's my W. W is going to be a vector living in this two-dimensional space. So W now is 2 by 1. If we go back to this picture, then V would be a 5-dimensional space, wouldn't it? It would be containing vectors that are 5 by 1 vectors. W would be containing vectors that are TWO tall and they're narrow. They're just column vectors, aren't they? I'm starting with a 5-dimensional vector, but what I'm saying is there's probably going to be vectors in this 5-dimensional space that will map into the 0, 0 vector, meaning that A matrix is going to have a null space. It's going to have vectors that I can find that are 5 by 1, that are not all 0 elements, that when hit by A will map me into the additive identity or the origin or the 0 vector in W. And I think that's maybe, well, we can, so the notation, let me give you another thing to think about besides matrices before we stop, but the notation here is T is this linear map taking V to W, and now by definition what I'm saying is the null space of T is defined to be those vectors in V. In the matrix case, those were 5 by 1 columns, such that TV is equal to 0, where T is some operator and they map into 0. One example that's different from a matrix is the differentiation map. And what was that? Well, that was, let's say, if we take a polynomial and we differentiate it. Now, what when we differentiate gives us 0? Constants. So now in this entire domain of polynomials of any order, the pieces of those, or those polynomial functions that are in the null space of this differentiation map, are the constants that are living in this big vat of polynomials. So you have 1 plus x, you have 2 plus x squared, you have x cubed. All of those are being stirred around in this big mix of script P of R. And in that big soup pot, you might have a 3. You might have a 7. You have all these real numbers in that pot. You differentiate those, and those are in the null space. Does that make sense? Of the differentiation map. We'll pick up at that point on Monday. Wow, I'm so confused. Enjoy your weekend.